Hello everyone, I am Dr. Fawzul Atiq. I am giving some series of lecture for the course Discrete Mathematics. So we are in the first unit, and in the previous lectures we discussed about the some quantification method, right? With the help of some quantifiers, which are universal quantifier, then existential quantifier, and the uniqueness quantifier. So we have discussed these things in our previous lecture. In today's class, we'll start with that like some expressions are there which involve this quantifier, and if you find the negation of it, what will happen in that case? So negating quantified expression, right? Now look at this example. Every student in your class has taken a course in calculus, correct? So how you can write it? You can write it as for all x px, where px is the statement that, so you denote a propositional function that x has taken a course in calculus and the domain consists of all student in your class, and then you are saying that for all x px. Now in your class it may be true that every student have taken a course in calculus, so you will immediately say that for all x px is true, because it's a true fact. In your class it may be the case. Now suppose this case is not true. That means what? You must have a counter example, right? So that means this true will become false if you have a counter example. Now counter example means what? There must exist one px for one, there must exist one x for which it is not true, correct? So there must exist in one x such that px is not true. So if you get some x, particular x1 for which this is false, that means for all x px will be false in that case. What does it mean? There must exist an x for which not px is true, therefore, right? So therefore, if I want to say that, what is, if I negate it, what is the negation of this statement? Negation will become now, there exists an x for which px is not true. That means not px is true. There exists x not of px. This will be the negation of it, right? So therefore, if we say that this one, so the negation of this statement is, it is not the case that every student in your class has taken a course in calculus, and it is not the case that every student have taken, means there must exist one counter example. So one example is enough. So what you will say in a short way, so you will say that there is a student in your class who has not taken a course in calculus. Now there is a student means there exists, and not taken a calculus means not px is true. That means px is not true. That means not px is true. So there exists an x such that not of px. Right? You can denote in this way. So there is a student in your class who has not taken a course in calculus, and therefore we can write there exists x not px. So we got, if I have not of, if I have for all x px, this is a proposition, and what is the negation of it? That negation of for all x px is equivalent to there exists x not of px. Easy? We understood? Okay, look at this example. Now we say that there is a student in your class who has taken a course in calculus. There is a student in your class who has taken a course in calculus. So how you will write it? So you will write it as there exists x px. This statement you can write it as this way. There is a student in your class who has taken a course in calculus, where px is the student that x has taken. Px is the statement that x has taken calculus. So you can denote it this way. Now, what should be the negation of it? Now you are saying there exists a student who has taken a course in calculus. Now negation it, if this is true, then how you will make it, it is false. So this there exists x px is false whenever px is false for every x, isn't it? So whenever px is false for every x, what does it mean? That for every x px is false, right? For every x where px is false, that means what? For every x not p is true. For every x not p is true, right? And then the negation of this statement will become what? Negation of this statement will become that every student in your class has not taken calculus. This will be the negation of it. I hope you understand. And how you will denote it? That for all x, not of px. Then only it will be true. Na? So this one, if this is true, this will become false. This is the exactly negation of it. Right? So therefore, the negation of this statement is every student in your class has not taken calculus. And this you can denote it as, so there exists x, not there exists x qx, negation of it, it will become for all x, not of qx. We are done. So this is how you can find the negation of a quantified statement. Right. So we got actually two rule, or both of them together we can write it as not, if I have for all, negation will become there exist. Right. And px will become not px. So there exists x, not of px. For all x px, negation of that. So for all, if I have, it will become there exists. And if I have there exists, so not of that will become for all. And inside thing will become negation of this. So if we have qx, it will become not of qx. So it is the same kind of law, right? So if I have or, if I do negation, it will become and in De Morgan's law for proposition. If I have union, then in the complement, it will become intersection, De Morgan's law for set. Now these two are called De Morgan's law for quantifiers. If you have for all, it will become there exist. If you have there exist, negation will become for all. I hope it is clear to you. So these two are called the De Morgan's law for quantifiers. I hope this is clear. Now we'll do some examples. Now there are two statements. What are the negation of them? So what are the negation of the statement? There is an honest politician. There is an honest politician. So what does it mean? There is an, that means there exists an x such that px. Right? What do you mean by px? Px is x is honest politician. Now what is the negation of it? So if I have px is such that x is honest politician. So there exists px. You can denote this one as there exists px. Now what is the negation of it? So we all know the De Morgan's law for quantifier. So negation will become, this is equivalent to there exists will become for all x. Then px will become not of px. This is the De Morgan's law for quantifiers. Now px means x is honest. Not of px means x is dishonest. And it means for all x, not px. What does it mean? It means that for every politician, like if the domain is all politician, then you will say that every politicians are dishonest. Right? So you can immediately say that the negation of the statement is every politician is dishonest, just by applying the De Morgan's law for quantifier. So initially I had there is, and that means there exists an honest politician. Negation of if is for all, so every politician, and honest politician, opposite of it, it is dishonest. So every politician is dishonest. Done. We have one more example. It says all Indians eat chicken. Now we have all Indians eat chicken. What is the negation of it? Now all Indians means for all, right? So here you have, here it is given as for all x, q of x. All Indians eat chicken. Qx is the such that eat chicken. X eats chicken. What is the negation of it? The negation of it will become by De Morgan's law of quantifier. It will become there exists an x, not of qx. And what does it mean? So there exists an Indian, not of qx, who does not eat chicken. So the negation of all Indians eat chicken will become there is an Indian who does not eat chicken. Negation is done. I hope these are clear. Easy. We have one more example, that is mathematical expression. What is the negation of this statement? For all x, x square greater than x. And what is the negation of this one? There exists x not x square equal to 2. Very easy. So I have, this is even very easy. So for all x, x square greater than x. You have to find the negation of it. That means you have to put a negation here. What is the negation? We know that if I have for all x, this will become there exists x. Then this will become not of x square greater than x. Right? Now not of. So there exists x, I'm keeping it as it is, but not of x square greater than x, greater than x. What is the negation of it? Yes, the negation will become x square is less or equal to x. So there exists x square less or equal to x. This is the negation. The second one is even more easy. There exists x square is equal to 2. What is the negation of it? So put a negation sign. This is equivalent to there exists will become for all x, then not of x square equal to 2. So this will become not of x square equal to 2 is x square actually not equal to 2. We are done. Easy, right? So this is how you can find the negation of a quantified statement using De Morgan's law for quantifiers. Okay, one more example. Now see that show that these two are logically equivalent. So we have done this kind of example previously as well. How do you do that? Using some propositional equivalence formula, we can do that. Now we know that the De Morgan's law for quantifiers also. So make the video pause and try your own. Unless you try, you'll never learn. Okay, so you make the video pause and do it. I will also do it parallelly. Okay, so I have not of for all x and px imply qx. I have to show that this is equivalent to this quantity. What is that? So this is equivalent to, first what I'll do, I know that this is p imply q, px imply qx. It is equivalent to something. What was that? I said it very, very important, right? In previous lectures also we have used them. Implications law, what is that? So I am keeping the first few things as it is. And this inside portion is equivalent to not of px or qx because of this implications law. We all know, correct? Now I can apply the De Morgan's law for quantifiers. So I have for all, the not of for all. So it will become there exists x. Then this not will be here and then not of px or qx. But not of this one. What is that? So something or something. What shall I apply? De Morgan's law for proposition. So this will become there exists x. So De Morgan's law, what it says? If I have or, this will become and this individually they become negative negation of it. So negation of negation px. What will happen? Px. Or will become and negation of qx. Done. Actually, we are done. We want to prove this only, na? That for negation of for all x, px imply qx is equivalent to there exists x, px and not qx. Done. I hope you understand this proof, but you should practice by your own. Okay. Now we have some English sentence. We have to convert them into logical expression because in many places you have to do it, right? In your if you want to execute some kind of English statement in computer and you want computer to do it logically, you have to convert it into a logical expression, right? So how do we do that? Here the first question is, every student in this class has studied calculus. So how do you prove it? You have to write it using like predicates and quantifiers. Predicate means some propositional function kind of a thing. So what we'll do, so we have to define a propositional function first. Suppose Cx is the statement that x has studied calculus. Right? Suppose Cx is the statement that x has studied calculus. Then how you prove? Every student in this class has studied calculus. How do you prove that? How do you write it? Every student means for all x Cx, where the domain is all student in your class. So you will write it as for all x Cx. It means that every student x has studied calculus. That means every student has studied calculus. So the for Cx, the domain is all student in our class. Yeah, so you see, so you can write it as for all x Cx where the domain consists of all student in your class. Done, right? So in this way you can write an English sentence into a logical expression using quantifiers and predicates. We will discuss a lot of example like that in the another video. So before that, we want to discuss one more concept called nested quantifiers. What do you mean by nested quantifiers? So two quantifiers are nested if one is within the scope of the other. Right? So what does it mean? Suppose in some expression you may have two different quantifiers. So two of them are for all. So this is one of them is within the scope of the other. You may also have that for all x, there exists y, right? There exists uniquely z. So this is one of them is within the scope of the other. So this kind of quantifiers you call them as nested quantifiers. Correct? So the example is assume that the domain for variable x and y consists of all real numbers. Then the statement for all x for all y, x plus y is equal to y plus x. And what it says that x plus y is equal to y plus x for all real number x and y. So it is a nested quantifiers, right? So for all x, for two are there, one is within the scope of the other. So this is an example of a nested quantifier. Then we have one more example, that this one for all x there exists y, for all x there exists y, x plus y equal to 0. What it means? It means that for every real number x, where the domain is all real number, right? So it says that for every real number x there is a real number y such that x plus y equal to 0. It says this thing, right? So for every real number x there is a real number y such that x plus y equal to 0, and which is true also, right? Because for every real number, you check any real number, maybe 5, and for that particular real number you have a one real number which is minus 5, such that one real number y which is minus 5, such that x plus y is equal to 0, 5 plus of minus 5 equal to 0, which is true. So therefore this is a nested quantifiers, one is within the scope of the other. I hope this is clear. Now one more expression, maybe translate this statement into English sentence. So you have a logical expression for all x for all y. Then if x greater than 0 and y greater than 0, then xy is less than 0. Where the domain for both variable consists of all real numbers. So what do you mean by that? Now see, for all x for all y, it means what? For every real number x, so it means for all x for all y. That means for every real number x, for every real number y, then this is the if condition, this and y less than 0. That means if x is greater than 0 and y is less than 0, right? Then it implies that their product is less than 0. Yes, it is true, we know it, that if I have for any real number, if one is positive and one is negative, then their product is negative, right? So this expression says that if x is positive, so for every real number x and y, if x is positive and y is negative, then xy is negative. Done. So this is how you can read a logical sentence into an English sentence, right? Where the quantifiers are in nested quantifiers. Okay, next one very important concept called the order of quantifiers. So the order of quantifiers actually very important. It matters a lot. It will change the truth value, you know. So the order of the quantifier is important unless all the quantifiers are universal quantifiers or all of them are existential quantifiers. If you have the same quantifier, then order may not be matter. But if they are different quantifier, like for all and there exists x, if it is a combination, so then these orders matter, right? So it or truth value will change. We'll understand this through some example. Look at this. So this one is actually true for both. So for all x for all y, pxy, where pxy is x plus y equal to y plus x. So in this case, whether you are taking x first and y second, it does not matter because both of them are the same quantifier, universal, for all and for all y. So we know that for every x and for every y, x plus y equal to y plus x, right? So we can also say that for every y and for every x, x plus y equal to y plus x. It is true for all. So we can say that for in this case, this is a true and this one is also true. Both of them are true actually. For all y, for all x, pxy. Both of them are true in this case. But it may not be the case in other cases. Because here both of them are the universal quantifiers, so both of them are same, so it does not matter. But look at this example. Let qxy denote that x plus y, qxy is such that x plus y equal to 0. Then what you are saying? That for all x, there exists y, qxy. Is it true or not? Yes, it is true, because for every x, there is a real number y such that x plus y equal to 0. We have discussed already. So this is true for any real number. But what about this one? There exists y for all x, q of xy. Now what does it mean? This means that there is a real number y for which every x is such that x plus y equal to 0. Do you have such y? Do you have such real number for which you have a single real number for which if you add any real number you will get it 0? Is it possible? It's not possible, right? So this case it is a false one. So see how the orders matter. Correct? So the order of quantifiers actually matters. It can change the truth value. Whereas in this case it is true, in this case it is false. I hope these are clear to you. Now we have one more example. Oh, sorry. So this one we have done. Look at this example. We are about to finish this lecture. So we have for all x, for all y, there exists a z such that qxy means x plus y equal to z. Now is it true or false? It says that for every real number x, for every real number y, there exists a real number z such that x plus y equal to z. Yes, it is true. So take any two real number, maybe 5 and 7. So there exists a real number which is 12 such that 5 plus 7 is equal to 12. Yes, this is true. For any two real number, there is a real number whose sum is that real number. It is true. Therefore, this is true. But what about this one? There exists a z for all x, for all y, x plus y equal to z. What is the truth value of this one? It says that there is a z, there is a particular z for which if you add any two real number, you will get that is equal to z. Is it possible? It is not possible, right? You do not have a single z for which if you add any two real number, that sum is that real number. No, it's not possible. So in this case, it is a false one. Right? So see again how the orders matter. You have these things, there exists z at the end, right? That was true. Whereas if I change the order, I made it, this is in the beginning and then this, it becomes false. So that meaning is getting false. So this is false. Right? I hope you understand. So this is how we have done. This is the complete answer as you discussed. All the content I have taken from this book only. I hope you enjoyed the video. I hope these videos are helpful for you. I hope you are learning. And always I'll say that please do practice some examples. Unless you practice by your own, you will never learn. You may understand that I have understood everything. You may think that you have understood everything. But if you don't practice, you cannot apply. Please do practice. Give your feedback. If you want some different way of doing it, some problem solving session if you want, that also you can write. Right? Thank you very much. We'll meet in the next video.